Welcome, ladies and gentlemen. Good morning. May I have your attention, please? Okay, let's get going right away. We've got a big day. We're going to develop and apply the fundamental theorem of calculus, and yes, it is as important as it sounds, okay? So that's what we have to look forward to. But first, we want to make sure that we're comfortable using the mean value theorem. So we saw last class how the mean value theorem, right, was a way to determine when the instantaneous rate of change of a function was equal to the average rate of change of the function over the interval. And so long as my function f is continuous and differentiable on the open interval, then there's guaranteed to be some place, x equals c, where the slope of the tangent is the same as the slope of the secant line connecting the endpoint. However, we must first check to see that my function f is continuous and differentiable over that interval. So let's go ahead and take a look at our first one. So here we go. Does the mean value theorem apply to f of x equals tangent x on the interval 0 to pi? So did the mean value theorem apply for that first function tangent of x on 0 to pi? Riley? No, how come?
Because there's infinite discontinuity at x equals pi over 2.
Absolutely. And so, no, we cannot apply the mean value theorem to the function y equals tangent of x on the interval 0 to pi because we know there's an infinite discontinuity. Awesome use of the language. There's an infinite discontinuity at, and I better use a different color here, at x equals pi over 2. And since there's a discontinuity on my interval a to b, then the mean value theorem, right, does not apply. That doesn't mean that there might not be, right? There might not be a place where the slope of the tangent is equal to the slope of the secant line. It just means that we're not guaranteed to have one such point, at least one such point. All right, so no, we can apply that. Raise your hand if you had no for the first one. And it turns out here there's not one, okay? There's not. Let's go ahead and take a look at our second one then. So does the mean value theorem apply to f of x equals cosine of x on the interval 0 to pi? Meg?
Yes.
Yes, it does. We have a smooth, right, differentiable, well-behaved function that's continuous on my interval 0 to pi. And so I know the mean value theorem guarantees the existence of at least one x value on my interval a to b, in this case 0 to pi, where the slope of the tangent is going to be the same as the slope of the secant line. So what I've done is I've drawn in a slope of the secant line connecting the endpoints. Our job is to, 1, figure out the slope of that secant line, and then 2, figure out where the slope of a tangent, that is f prime, the instantaneous rate of this change of the curve, is equal to the slope of that secant line. So first, let's do my slope of the secant line calculation. We know the slope of the secant line is given by f at b minus f at a all over b minus a. For this particular function, cosine of x, I know cosine of b is the same as cosine of pi. And so we'll go ahead and evaluate my slope of the secant line as cosine of pi minus cosine of 0 all over pi minus 0. So it looks like cosine of pi is negative 1 minus cosine of 0 is 1 all over pi. So I'm looking to see where the slope of the curve, right, the slope of the tangent line is equal to negative 2 over pi. But first I want to check and see who got this far. So who got a slope of the secant line is negative 2 over pi? Great, that's my average rate of change of the function over the interval 0 to pi. I want to see where the instantaneous rate of change is equal to that average rate of change. So what do I need for instantaneous rate of change? Right? What expression tells me about the instantaneous rate of change? Nikki? Absolutely. We want to see where f prime of x is equal to negative 2 over pi. So let's go ahead and find the derivative of f of x. So f prime of x is the derivative of cosine of x. So that goes to what? Opposite sine of x. Is that right? Opposite of sine of x. And we want to see where opposite of sine of x is equal to negative. Oh, I'm getting excited about the pi. I like pi. Is equal to the slope of the secant line, negative 2 over pi. So let's go ahead and solve. We know if negative sine of x equals negative 2 over pi, we're looking to see where sine of x equals positive 2 over pi. And 2 over pi, right, is about 2 over 3, so about 2/3, about 0.26, 0.6, right, 0.5 something. And so we know that this definitely has solutions. right? And we want to see where they are. So how do I solve sine of x equals 2 over pi algebraically? Right? What do I do procedurally to solve for my angle x here? How am I going to solve that? Sophia? Absolutely, right? Inverse sine undoes sine of and gets that angle alone. So we'll take the inverse sine of both sides. That will get x alone. And so I'll get x is given by the inverse sine of 2 over pi. Since this is not an exact value from our 16-point unit circle, right, we're not going to get a root 3 over 2 or a pi over 4 or anything like that from our special 16-point unit circle. We have to go to the calculator to get an approximation, but we want to make sure that we are in radian mode. So everybody, let's do a quick check and make sure that we're in radian mode, and we'll determine what angle x produces a value of sine that is 2 over pi. So here we go, inverse sine of 2 over pi. And it looks like at about 0.69 radians, at about 0.69 radians. As I look at my picture, right, as I look at my picture, where this is 1, 2, 3, there's pi. So this is going by ones. Does it appear as though at x equals 0.69, that seems reasonable for a place where the slope of the tangent, right, the slope of the tangent is equal to the slope of the secant? Well, about 0.69 would be, if that's 1, then that'll be about right there. Well, by golly, it does look like that. And if I were to ungroup this, group it, and clone that, if we could just slide that up, right? And so it just touched the curve, to represent the slope of the tangent line, then it looks like, by golly, right about there, about 0.6, right? There's one x equals c value. Michaela.
What if the interval was 1 to pi? How would you find where the tangent line is parallel to the secant line?
That's a great question, and exactly what we still need to do, because we've only found one place where the slope of the tangent is equal to, and as you look visually, right, Michaela notices there's more than one place, right? Isn't there another place where the slope of the curve is equal to the slope of the secant line? Yeah, over, well, about somewhere around here, isn't there? Does everybody see that? So what do we do to find my inverse sine is a function, right? It's restricted domain and range so that it only spits out one value. But we see that there's going to be another value on this interval. So how do we find it? What do we do to find that? Hayden?
The intervals, can't you just take the value we just got and subtract that from pi?
You can subtract that from pi. And so when you're evaluating sine, right, inverse sine or sine function, we know that the sine of 30 degrees, that is pi over 6, is the same as the sine of 180 minus 30 degrees, that is 150 degrees. Why, yes, it is. In each case, the value of sine is 1/2. And so we can generate additional values by taking 180 minus, right? And then if we were unrestricted here, we could go 180 plus and then 360 minus, and so on and so forth. Absolutely. Thank you, Hayden. So this will give us one value, about 0.6901. And remember, right, we want to keep our decimal places. So how do we get the other one? In short, 180 minus, right? Or in this case, pi minus. Thank you, Hayden. And I'll do x sub 2 equals pi minus 0.6. Is it 09 or 9? 69. That's pretty sweet. And so that's about, I'll do pi minus answer, right? So about pi minus answer, and so about 2.45, and let's go ahead and visually check that out. All right, here we go. 1, 2, 2.45. Well, that does look reasonable, so we'll go ahead and clone another one of those, and right about down there, and so it looks like my x sub 2 looks to be about here. So in this case, there were two places where the slope of the curve was the same as the slope of the secant line. That's pretty awesome. What questions do you guys have about our Bellwork today? So that's the mean value theorem. Remember, you can only apply the mean value theorem, right? It only guarantees the existence of a c value on the interval a to b if the function is continuous and differentiable on that interval. Now is the point of number 1, right? All right. Awesome work, you guys. Let's go ahead and box that. And we'll go ahead and take care of our OTL number 6. This does not include the definite integral practice number 8. That was for a stamp, and so you don't need to pass that in. You may keep that. But we do need your OTL number 6. Make sure that you have your name first and last, 2A, and number 6 clearly labeled on top of your OTL. There's no picture on the half sheet, right? So you can just pass. You don't need to staple unless you have multiple pages, and then I would ask that you staple them together. Give yourself credit for those you complete out 20, please. Divide, enter, multiply by 2, and let's box them in a canvas score nice and big on top, down to the nearest half point. And let's go ahead and pass it in now, please. Thank you, front rowers, for making sure they're facing the same direction. I appreciate your help. Thanks, you guys. Thank you, Savannah. Okay, ladies and gentlemen, I appreciate your help with that. So, we want to make sure that you're comfortable with your antiderivative rules, and we've seen this the past 3 class periods. And so I just want you to look. You don't have to write this down. We know that an antiderivative, that is an indefinite integral for a power function x to the n in general, is gained by reversing our derivative shortcut rule for a power function. That is, exponent times the base raised 1 less. Reverse and undo, we would add 1 to the exponent and divide by the new exponent. So we know this will be x to the n plus 1 all over n plus 1. That is, add 1 to the exponent, divide by the new exponent. Don't neglect to include a plus c. We also know that the power rule falls short when integrating the inverse power function, the reciprocal function, 1 over x to the first, because when I add 1 to the exponent and get x to the 0, that's fine, but when I divide by 0, right, then we run into all kinds of problems. We can't do that. And so we have a different rule, ln of absolute value of x plus c, and we talked about the absolute value bars originating to preserve the domain of the original integrated function. We're going to see that later when we go and do some definite integral calculations using antiderivatives. And so that's where we're headed today, and we're going to come full circle with our fundamental theorem of calculus. So I'm super excited about today. You guys are on the edge of something really big, okay, really big, and so I'm really excited about today. So let's get together and feel all right. Yes, that's right, 5-6. 5-6 is the fundamental theorem of calculus, and we've got a lot of opportunities for stamps here. So let's take a minute and get our stamp eligible items. So 2E, 3C, 8B, 11B, and 17. So we've got up to five stamp eligible items in class. Okay, we're going to come together and we're going to do several of our fundamental theorem of calculus application problems. At the end, we're also going to take a look at the tech tip, but we're not going to do that now. Instead, I'm going to pause the recording and we're going to go ahead and investigate our 5-6 first. And then as we get towards the end, we need about 10 minutes, a little bit more than 10 minutes together towards the end. So we've got just about an hour, okay? Let's go. I'm going to go ahead and pause the recording. Look out. One of them, perhaps. So today's activity was fundamental to our evaluation of definite integrals because it provides a connection between antiderivatives, that is indefinite integrals, right, and the exact area underneath the curve, f of x, on an interval a to b. And so we saw that we could find those x equals c values, right? Those c values, those x values that when connected to the integrand function would give us the perfect height of a rectangle, such that when multiplied by the width of that rectangle, delta x gave me the exact area underneath the curve, even though the original curve was, well, curved, right? Irregularly shaped region, I could still get one rectangle that found the exact area underneath the curve if I could just find that special c value. What was the key to finding that special C value? The mean value theorem. So the mean value theorem provided us with the missing link in order to find the exact height, the perfect height of the rectangle, such that when multiplied by the width of the rectangle gave me the exact area underneath the curve. So we've got a fundamental theorem of calculus now. If f is an integrable function, that means there's an antiderivative for f, and it's called g, then we can get the exact area in between my function f and the x-axis over some interval a to b by finding the antiderivative function g, evaluating at the upper limit, evaluating at the lower limit, and subtracting the two. Now we have a means for evaluating a definite integral, which represents the area underneath the curve, right? Exactly and algebraically using an antiderivative, without having to use any sort of tech tip or trapezoids or rectangles, right? That's what is so powerful about the fundamental theorem of calculus. So we're not going to go and do all these. I want to make sure that we have plenty of time for our closer. You can check each of these by using your tech tip, okay? So we'll do one for closer. If f is an integrable function and g of x is an antiderivative of f, that just means g of x is an antiderivative of f, then the integral from a to b of f of x with respect to x equals blank. Don't say it out loud. And then lastly, let's go ahead and apply the fundamental theorem of calculus to evaluate that definite integral. Remember, the definite integrals are easy to recognize because they have limits on your integral symbol, right? They have the limits in front of the integral symbol. And the result is a number, a numerical quantity that represents the area in between that function and the x-axis over that interval a to b. Okay, ladies and gentlemen, let's go ahead and share the conclusion then of the fundamental theorem of calculus with the correct f's or g's or b's, right? So what's that going to look like? If g is an antiderivative for f, then the definite integral of f with respect to x on the interval a to b is given by Hayden.
G times x plus c.
So my antiderivative for f is g, right? And then to evaluate those last ones on number 18, right? You went and found
G of b minus g of a.
absolutely. So just g of b minus g of a. That gives me the exact area underneath the curve, right? Underneath the curve at over the interval a to b. Raise your hand if you have g of b minus g of a. G of b minus g of a. Awesome. Then let's go ahead and apply it. So in order to evaluate this definite integral exactly and algebraically, I can do it without a calculator by using an indefinite integral and evaluating that antiderivative at the upper limit, the lower limit, and subtracting the two. So let's go ahead and check to make sure we have the correct notation. I'm going to evaluate this definite integral by first finding an indefinite integral, an antiderivative function for 6x squared. So I'll use the power rule and a constant multiplier. That would be x cubed over 3 times the 6 out front. So I'm getting 2x cubed as an antiderivative function. Are you guys getting that? Right? Now we would have a plus c here, except I know that in our subtraction, right, whatever constant was added on to my function, when subtracted off, is going to cancel itself out, and so I'll be left just the numerical quantity, so I don't need to include that. Our notation here we can write with this bar, and then my lower limit and my upper limit. And then I'll evaluate that antiderivative function, so I get 2 times 3 cubed minus 2 times 1 cubed. For my limits, or 1 to 3. So upper first, then lower, then subtract last. And I get 3 cubed is 27 times 2 is 54 minus 2. Go ahead and raise your hand if you already had 52 units, 52 square units. That's awesome, you guys. That's a fundamental theorem of calculus. And you can always tech tip it by using your Math 9. Awesome work, you guys. Don't forget OTL 7 for next time, and I'll go ahead and save the recording.